So in the last video we saw how we could take an alternating current and an alternating voltage signal like this one here that might have a high maximum voltage like 240 volts, and we could convert that into something lower and more useful for electronic devices like 12 volts by using a transformer. And this has made some progress in terms of our overall gain, overall aim of creating a constant DC low voltage signal. However, we're still some way off because we still have an alternating signal. So in this video we'll be looking at rectifiers, which are a way of converting an alternating signal into a current that only moves in one direction. So because the sum of all the voltage gains around the circuit equals the sum of all the voltage drops around the circuit, voltage gains being the potential difference supplied by this source here, voltage drops being the potential difference created by this load here, whatever signal we have at the input voltage is going to have to be equal to whatever signal we have at the output. Okay? If we have 12 volts coming in as the voltage gain here, we're going to have 12 volts across here as the voltage drop. Okay, so that input and that output signal are going to be the same. But we want to change that output signal. We want to get rid of this negative component. And so how can we do that? Well, firstly, let's go back and think about the fact that the electrons in this circuit are moving backwards and forth. Okay, so they're oscillating like this. But we want them, if we want to have only a positive voltage across here, we want the electrons to only be moving in one direction. We want to eliminate the component where they're moving back in the opposite direction. So to limit the motion of electricity to one direction, we use a diode. We insert a diode into the circuit like this. What happens? Now, conventional current can move in this direction, okay, can move in the direction the diode is pointing, but it can't move back in this direction. Okay, so we will get, when the voltage here, the input voltage is positive, we'll get a conventional current being pushed in this direction, current flowing through here, so that then there is a voltage drop across this resistor. If, however, the input voltage is negative, conventional current will try and push back in this direction and won't be able to flow. Okay? When that occurs, there'll be no current flowing through this resistor, and by V equals IR, if the current through the resistor is 0, then the voltage across the resistor is also going to be 0. And we can see that here. Okay? This output voltage now will only contain the positive sections of the input voltage. As far as what is the magnitude, the peak voltage here, well, actually that's only going to be 11.3 volts. Okay? Why is that? Well, we can think about the situation where we have 12 volts at the input here. Okay, so if we've got 12 volts being supplied, just take that as a single example, 12 volts coming into the input. Okay, what's going to happen? We're going to have a forward biased diode, and most diodes, when they're forward biased, will have a voltage drop across them of 0.7 volts. Okay? As the current flows through in the forward direction, there is always a voltage drop of 0.7 volts across that diode, which will mean that we have 12 minus 0.7 equals 11.3 volts at the output. Okay? So when we have the maximum of 12 volts at the input, we only end up with 11.3 volts at the output. So that's why that's the peak voltage observed here. So if this is what's occurring across the output, and we're getting these positive voltages across the output, a question could be, alright, if the sum of all the voltage drops is equal to the sum of all the voltage gains is equal to the sum of all the voltage drops. This is at the moment the only voltage drop that we're observing, but we've still got all of this voltage gain, still got the same signal coming to the input. where is the rest of the voltage drop? Okay, so the rest of the voltage drop is going to be across the diode. And the voltage drop across the diode is going to look like this. Okay, cool. When we have a negative voltage at the input, we have all of that voltage appearing across the diode. Okay, why is that? Well, look at this here. Okay, when we have a negative voltage, we have the current trying to flow in this direction. By V equals IR, we have 0 volts across here. There's 0 volts across the resistor. There's going to be the rest of the voltage drop across here. Okay, and if we have a positive voltage across here that is less than 0.7 volts, okay, that's still less than the switch on or the forward bias voltage of the resistor of the diode. So we have a maximum voltage here of 0.7 volts. Okay, it takes up to 0.7 volts before that diode will start to conduct current. If we want to try and add these two signals together, okay, we'll see what happens. We add the signal that we have here at the output by folding this piece of paper, like so. We add that to the signal at the diode. Okay, we should see that when we add those two signals together, the sum of all the voltage drops again is equal to the sum of all the voltage gains. Okay, it's just where those voltage drops occur that changes. Depending on where in the cycle we are, the majority of the voltage drop might be across the diode, or it might be across the output resistor. Anyway, the important thing is that by adding this diode into the circuit like so, we can achieve an output signal that is purely positive. Okay, and that means current is flowing through the load resistor in only one direction. We're closer to getting a direct current. So to wrap up this video, I recommend that you re-watch it. You sketch this circuit diagram with the diode. You sketch the input signal, the output signal, and the voltage across the diode. Okay, and make some comments about how those relate to each other. Okay, so comment on the fact that the sum of all the voltage drops is still equal to the sum of all the voltage gains, but it just changes where they occur. And comment on the objective, which is getting the current flowing purely in one direction. In the next video, we'll look at how we can turn this still time varying signal like this into something a bit more constant.